Good evening, Lower 6. So we've come to the last lesson on electric circuits, and in fact the last lesson on the Lower 6 part of the A-level physics syllabus. So well done getting this far. The last lesson is going to be talking about EMF, or electromotive force, and internal resistance. This is quite an important topic. It's important because there's lots of questions. It's a good one for setting problems. So there's lots of questions that can be asked about it on A-level exams. There's also going to be a required practical on it, which we'll do in the autumn term. And also, it's something that you wouldn't have covered, at least in any great detail, previously at GCSE. So it is important that you understand what's going on here. And if you do have any problems or any misunderstandings, don't hesitate to contact me and get in touch and ask for some help. So, EMF and internal resistance. Basically, what we're going to be talking about tonight is power supplies for circuits, in particular cells, but a lot of this will also apply to transformers, power packs, and so on. Okay, but in particular, we're going to be talking about cells. So what we've got here, very basic circuits. We've got an ammeter, we've got a light bulb, and we've got a 1.5 volt Duracell cell. The light bulb's not on because there is current going through it, but there's not enough voltage to switch it on, so you're not seeing it glowing. But there is current flowing. There's about half an amp or 0.45 amps flowing through this circuit at the moment. So, what's powering the circuit, of course, what's supplying energy to shunt all these electrons around is the cell. So I'm going to take the cell out of its housing just for a moment and just talk about electric cells. So, as I'm sure you're all aware, cells come in a variety of shapes and sizes. Okay, that's a D cell, and it's a 1.5 volt cell. It has a positive terminal and it has a negative terminal. And if we place this in a circuit, we know what's going to happen, okay, because we've talked about it before. Let's say we put it in a circuit with a resistor and connect it with wires, okay. What's going to happen is that if it's a closed circuit, current will flow from the positive terminal around the circuit to the negative terminal. Now, by current, I mean conventional current. What's actually happening is that the electrons move the other way in the opposite direction from the negative terminal to the positive terminal. Now, cells work by basically a chemical reaction happening in the cell. You don't need to understand the details of this chemical reaction for A-level physics, so don't worry about the exact mechanics and chemistry of how cells are working. But basically, this chemical reaction is transferring energy to move charge between the terminals. And by doing that, it's keeping this terminal negative and this terminal positive. So when electrons arrive, as they would do at the positive terminal, it takes these electrons and it moves them across to the negative side of the cell. Now, if you think about it, the electrons do not want to be at the negative side of the cell because negatives repel negatives. And so as soon as they're here, they'll try and find the quickest route back to the positive, which will be around the wire and through the circuit and back to the positive terminal. Another way of thinking about the cell, you can almost imagine it, if any of you have been sort of skiing in Switzerland or France or anything, you can always imagine the cell being like the ski lift, okay? So, when you're on the ski slope, the ski lift takes you up to the top of the hill. That's a bit like moving the electrons from the negative terminal to the positive terminal, giving them potential energy. And then you get to the top of the hill, and then gravity, if it's a ski slope, gravity will take you back down to the bottom of the mountain again as you ski down. And that's a bit like the electrons flowing back around the circuit and then returning to the positive terminal. So the cell's supplying potential energy, moving the charge across from one terminal to another. And we measure the amount of energy required to move 1 coulomb of charge by the EMF, or electromotive force. It's a slightly confusing name by having the word force in it, because it's nothing to do with a force, as in a force in newtons. It's really an energy, okay? It's the the energy required or the work done to move 1 coulomb of charge between the terminals. Now, I suppose if you're thinking about this technically, a plus 1 coulomb of charge would actually, if you were thinking about where it would move, it would go from the negative terminal to the positive, whereas the electrons go the other way. But don't worry too much about that. Okay, so the work done moving 1 coulomb of charge between the terminals, in other words, the energy transferred from the chemical supply, store of energy in the cell, is what we call EMF, or the electromotive force. Now, we have discussed electromotive force before when we talked about Kirchhoff's second law previously. So obviously the unit of electromotive force is the volt, the joule per coulomb, the same as the unit for potential difference. Okay, the difference between EMF and potential difference, in case you're confused, EMF is energy given per coulomb of charge. Potential difference is energy taken out per coulomb of charge, usually when you measure potential difference across a component in a circuit, because energy is being removed and changed into something else. Okay, so that's what we mean by the EMF of a cell, okay, the electromotive force of a cell. By the way, if you have a load of cells in series, okay, Kirchhoff's law says that the EMF would add up. So if you had two 1.5 volt cells in series making a battery, that would be 3 volts in total EMF. If you had them in parallel, it would be the same as an individual, because parallel, again, Kirchhoff's laws, it would be the same as an individual cell, so it would be 1.5 cell if you had two 1.5 volt cells in parallel. So that's EMF, or electromotive force. And in a minute I'll show you, well, in fact what I'll show you now is how we'd measure the electromotive force. Okay, so I'm just going to do that now. So what I'm going to do is I'm going to replace my cell back in its holder as such. I'm going to disconnect it from the circuit. Okay, so there's the connections for the cell, and all I'm going to do is I'm going to connect this to a voltmeter. So voltmeters normally measure potential difference, but if we just plug a voltmeter across the cell with nothing else in the circuit, what we'll measure is the EMF. Okay, so there we go. I don't know if you can see that. Hopefully you can see that there. It should say 1.46 volts, something like that. So that is the EMF of this cell, the electromotive force of this cell. Now, with it set up like that, there's no current flowing, okay? It's just the voltmeter connected to the cell. Voltmeters, in theory, have a huge resistance, okay? Unless it's a very cheap voltmeter, it'll have a huge resistance, which doesn't let any current flow through it, okay? Or a minuscule amount of current. So we don't need to worry about something we're going to talk about in a minute, which is internal resistance. So you're just measuring the EMF of the cell. Essentially, you're just measuring the difference in potential energy of 1 coulomb of charge from one side of the cell to the other. Nothing's actually moving in this setup because we haven't got any current flowing, but we're measuring the difference in potential energy per coulomb of charge from one side of the cell to the other, from one terminal to the other. Now that's EMF. Or electromotive force. Now, when we talked about Kirchhoff's laws and series circuits and so on before, we mentioned Kirchhoff's second law, which is the sum of the EMFs in a circuit equals the sum of the potential differences in a circuit. So if I was to take this cell, I'm just going to unplug it now. If I was going to take this cell and plug it into a resistor, what we might expect is that the EMF of this cell would equal the potential difference across this resistor if that was set up in a very simple circuit. And that would be true if there wasn't any what we call internal resistance in the cell. Now in reality, what would happen is that we've just measured the EMF of this cell was 1.46 volts. If you measure the potential difference across this resistor, it might be, I don't know, it might be 1.3 volts or 1.25 volts. It would be slightly less than the EMF of the cell. Now, why is that? So why is the potential difference smaller? Okay, well, it means that there must be potential difference somewhere else in the circuit. Energy must be being lost in the circuit. Now, the difference between EMF and potential difference, EMF is energy gained by a coulomb of charge in the circuit. Potential difference is energy lost. And if the wires don't have any resistance, and we've already taken into account the resistor, the only other place where energy could be lost is in the cell itself, which is almost kind of counterintuitive in a way, because you think of the cell as supplying energy, but the cell can also remove energy. Now, this is only true if there is a current flowing. Okay, if there is a current flowing, if there are electrons moving through the cell. Okay, the cell is part of the circuit, which means current flows through it. And just like any other part of the circuit, it has resistance. Okay, it does take some work to get the electrons through it, even though it's giving energy to the electrons. Some of that energy is actually lost in the cell when the electrons travel through. And let's say the EMF was 1.46 volts and the potential difference across our resistor was 1.26 volts. That means somewhere we've lost 0.2 volts. Now, we'd call these the lost volts, okay, for obvious reasons. So 0.2 volts of lost voltage. Where is that voltage lost? Well, it's lost in the cell itself when there's current flowing through it. And the reason why is that as the current flows through, if it's 0.2 volts, then every coulomb of charge passing through the cell would lose 0.2 joules of energy as heat energy would be used to heat up the cell as the electrons pass through. So a real cell, what you can think about it is being a combination of a pure cell, a perfect cell, with an EMF and a small resistor that are in series with each other. So think about this cell as being two components, a perfect cell and a small resistor, which is in series with it. Now, the internal resistance of these types of cells, well, we might measure it in a minute. It's not very big. Okay, it's going to be I think less than an ohm, but we'll see. Nonetheless, you know, if you've got a large current flowing, you could have a significant internal resistance in the cell. Okay, so in terms of calculations, there is a formula. This is all going to be on the sheet that you're going to be all on the notes that you're going to be given. There is a formula which is that the potential difference across the terminals of a cell would equal the EMF minus the lost volts. Okay, that's the basis of the calculations you'll be doing on internal resistance. So the terminal potential difference, the potential difference from one terminal to another would equal EMF minus the lost voltage. Okay, now the lost volts would be the current that's flowing, which would also depend on what you've got connected to the outside of the circuit. It would be the current that's flowing times the internal resistance. Okay, just from V equals IR. In this case, it would be V equals I times small r, because we use small r as the symbol for internal resistance. So the formula basically is that V, which is the terminal potential difference, equals EMF, which has a symbol epsilon, which is a sort of Greek letter that looks like a 3 the wrong way around. So V equals epsilon, EMF, minus I times R. And that's the formula for EMF and internal resistance. Okay, if you didn't get that, don't worry about it. It's on the notes, but I'm also going to show you practically what this means. What it means is that if you get current flowing through here, you get less voltage across the terminals than the EMF. So remember, we measured the EMF across here before of 1.46 volts. So what I'm going to do now is I'm going to connect it back into the circuit I had originally operating with the bulb and the ammeter. So let's shift that resistor out of the way. So I'm going to stick it back in here. No, this isn't the most visually exciting practical in the world, but nonetheless you will hopefully see. Now unfortunately I do have some slightly dodgy wires, which means that things do flicker about a bit, but okay, it's flickering about a little bit. 0.46 amps, so just less than half an amp of current flowing around this circuit at the moment. Now remember that between here and here before, when I was just measuring the EMF, I had 1.46 volts. So let's see what I'm going to measure now. So I'm going to plug my voltmeter across the terminals of the cell. There we go. So I had 1.46 before. I've now got, it's flickering a little bit, but round about 1.29 it's averaging. So that's a lost voltage of about 0.17 volts, isn't it? So 0.17 volts being lost in the cell as lost volts. So if I wanted to work out the internal resistance of this cell, what I could do is I could take, I've got the current, which was 0. Flick it a bit. It was about 0.45, wasn't it? 0.45 amps. Okay, so I could say 0.45 amps, and I've got, now if I take the lost volts, which was 0.17 volts, and I divide that by 0.45, okay, I get 0.37 ohms. So the internal resistance here, 0.37 ohms. Now, if I was to change that light bulb for a light bulb with a smaller resistance, I'd have more current flowing, and that voltage would go down. Okay, you see what the voltage is at the moment? It's 1.3 volts. So if I had more current flowing, this voltage would drop. In fact, I can show you that in a very simple way, by if I take this lead out of here and I short circuit the light bulb, so that I'll suddenly have a huge current flowing, and that will drop to a very low value. At the moment it's gone up to the EMF because I've disconnected the circuit, so it's gone back up to 1.45 volts near enough. If I plug this in here, okay, wow, it's dropped to, now we've got 2.3 amps now, and the voltage has dropped to 0.67 volts. So you can see the effect of the internal resistance there. Okay. So that was a simple experiment to measure internal resistance. Now, as I said, you will do a required practical on this next term. If you were doing this as a serious practical, what you would do is, rather than having a light bulb or a fixed resistor, you'd have a variable resistor here. And you change that resistance, okay? And by changing that resistance, you would change the current that's going through the cell. So you measure the current at different values. Then by measuring the current at different values, you would measure the voltage across the terminals. So you'd measure the current and the voltage simultaneously, and you'd be changing the current continuously by changing this variable resistor. Okay. So by doing that, you then draw a graph. And the graph would basically look like, I haven't got a copy of it here, but basically the graph would look like a straight line, but it would slope downwards. Okay, so if you did voltage on the y-axis, current on the x-axis, you have current going across, the voltage would slope downwards. Okay, and the gradient of that graph, again, this is explained on the notes, the gradient of that graph, or I should say minus the gradient of that graph, would give you the internal resistance. It means that you're taking more than one measurement, okay, which means it's going to be more reliable, more accurate. So, and you could also extrapolate it back to the y-axis, and you'd get the EMF when the current is 0. So that's how you would do that experiment. It's a nice little simple experiment, really, that you can do with a cell and a variable resistor and an ammeter and a voltmeter. Okay, that's basically it for internal resistance and EMF. I mean, the only other little bits and pieces that are on the notes, I do talk about, well, what happens if you've got cells in series and cells in parallel. I've already mentioned that a bit with the EMF before, but what about the internal resistance? Well, if you've got cells in series, the internal resistance, as you would expect, just adds up, like any resistances that are in series. So R would equal R1 plus R2 plus R3. So you get more internal resistance. If you put cells in parallel, on the other hand, the internal resistance drops. So if you had 3 identical cells in parallel, the total internal resistance, or the effective internal resistance, would be 1/3 of an individual cell. Okay, now that can be useful sometimes because you might want a large current from your cells, so you want to reduce the internal resistance. Of course, the EMF doesn't add up either. Okay, the EMF is just the same as one cell in that case, but the internal resistance drops by 1/3. I can give an example of where that's used. I think the cells in a car battery are arranged in parallel to reduce the internal resistance, which allows you then to get a very large current to produce the spark, okay, to start the engine. So, you know, in some circumstances it's useful to have cells not arranged in series but in parallel, because that reduces the internal resistance. Internal resistance you can think of as being a bit of a problem, really, for cells. It's something that reduces the useful energy output of an electric circuit, because what you want in an electric circuit is for the electrical energy to be transferred to the external load, to the resistor or the bulb or whatever it is that's outside the circuit. What's actually happening if you've got a significant internal resistance is you're heating up the cell, okay, which means that some of the energy is being lost. So there's another little section in the notes on power and efficiency, linked with internal resistance as well. There's also a section on the notes about calculations and problems that you might come across with EMF and internal resistance. Okay, that is it, I'm afraid, folks, for electricity for this summer. Obviously, I'm going to set you some work for the end of the week, and that's it. Then you're broken up for the summer holiday. When we come back in the autumn term, we'll try and do an end of topic test on electricity. In fact, there's 2 small end of topic tests on electricity, which I think will be quite useful. So if you do get a chance to do some revision on this topic over the summer, it would be useful. Especially any of you chaps who are thinking about doing the retake exam for your predicted grades. This will be on it, along with everything else we did in the lower 6 as well. I am going to try and send you before the end of the week as many sheets in terms of problem sheets, and also mark schemes as I possibly can, so you can check. You can do some sheets and also check your answers as well. I'll try and get that done for you for the end of the week. And the other thing is we will have a Zoom lesson on Thursday too. Okay, but that's it. Last lesson of the year, and hopefully the next lesson that we will have will be actually in a lab. Okay, and I will be there and you will be there, and that will be a big improvement, hopefully, than doing Zoom lessons from my dining room. Okay, folks, enjoy your summer, get this work done, and get as many problem sheets as you can possibly do over the summer, if you can. But obviously take some time off and relax as well. It's been an interesting year, I think it has to be said. Okay, thank you very much, and good evening.